Hello, welcome to Soft Papers channel. I'm Godfrey. In this video, I'm working out A2 Physics Paper 5. This is a paper for planning, analysis, and evaluation. May-June 2019, the paper it is. This is a variant 5.1. Paper is 1 hour and 15 minutes. No additional material required for this paper. It has only 2 questions, and we are going to be solving that right now. Guys, subscribe to my channel and like it. Share it with your friends if you find this video useful. Also, don't forget to hit the bell icon. And you will be notified every time I upload this kind of videos. Let's get started, guys. As I said, this paper has only 2 questions, question number 1 and number 2. And that is what we are going to be solving today. First thing is to understand what the paper requires of us in question number 1. So let's read the question together. A student is investigating the bending of a loaded wooden strip, fig 1.1. Shows a rectangular strip of width. The width is B, the thickness is T, overhanging the edge of a bench, of course at a distance L. Length L of a strip is unsupported. A load of mass. There are several measurements that we need to take into account there. B, T, and L, which is length. We also have a load of mass M is positioned at P. This causes the unsupported part of the strip to bend with the deflection S. S is distance we need to measure. This distance is shown. Of course, fig 2.1 is not drawn to scale. You should take note of that. It is suggested that the relationship between S and L is this expression here, where G is acceleration due to free fall and E is the Young modulus of the wood. Design a laboratory experiment to test the relationship between S and L. Explain how your result could be used to determine the value of E. That is key. You design a laboratory experiment and explain how your results could be used to determine the value of E. Remember, we are designing an experiment to test the relation between S and L, but we need to use our results to determine the value of E. Take note of that. You should draw a diagram on page 3 showing the arrangement of your equipment. In your account, you should pay particular attention to the procedure, measurements to be done, control variables, analysis of data, and safety precautions to be taken. Now, the best way to work out this question is to identify the quantities that are present in this equation. So let's look at the quantities. Once you get to know the quantity, then figure out the suitable apparatus that you need to use to measure the quantity that you have in mind. So here we have the mass here. We have load which has got mass M. So the first quantity is mass. Mass. You need to measure mass. Mass M. Mass M. Which is the best apparatus to measure mass M? Balance it is. The second quantity is S. Let me call it distance S. And the best apparatus to measure that is a ruler. The second was length L. Length L. You need a ruler also to measure the length L. There is width B. If you have forgotten width B is right here, and then we need also the thickness T right here. So what do we need to measure? What apparatus do we need to use to measure width B? The apparatus is still a ruler. What about thickness T? Thickness T. For thickness T, we need a vernier calipers. We need a calipers to measure that thickness. So these are the quantities that you need to measure. You can see you have B in the expression here. We have S, we have T, we have L, and we have M. G is a constant, and the Young modulus, we are supposed to determine it. We don't measure Young modulus. We are supposed to now, after you get all these other, measure all these other quantities, then we can use them now to determine the Young modulus. Determination is basically calculation. All right, so you have those apparatus, those quantities and apparatus in mind. So the next thing is to define the problem, and in the process of defining the problem, you're supposed to draw a diagram here. So when it comes to defining the problem, it may seem pretty obvious, but before we define the problem, let us think of the diagram, or think of how we are going to set up our experiment, because the success of your experiment or the success of your data collection depends on how you set your apparatus for the experiment and the procedure that you're going to be following. So I'm going to draw the data that I have in mind here, because from this I can see the plank of wood is on a bench, and therefore on this bench I need a G-club to hold this plank of wood in place, because without something to hold this plank of wood in place, once you place a mass here, the whole thing will go up and tumble. So you need a G-club there to hold this part of the plank of the wood in place. Then of course your mass is going to be right there. So our diagram is really going to be a simple one. Just draw the bench here. This is the bench. This is our bench right there. Just draw a simple diagram, and then there is our bench, and then this is our table here. This is our plank of wood. Of course, the plank of wood is going to bend when it's bearing some mass. So let me draw it bent when it's bearing some mass. And then of course I have my mass here. This is the mass that I'm going to be suspending on this plank of wood. There is a mass, so this is mass M. This is mass M. This is an extensible string. Let me just call it a string. The string is not extensible. String and hook. Initially, this was the direction of the wooden bar before it was bent. This is L here. This is length L, the length of the wooden bar before it was bent, right there. Then this distance here, this is S, the distance at which the block has bent. And then this is my G-club here. This is my G-club. to hold this in place. You label clearly. This is G clamp. Of course, this is the bench. That is the bench. So that's it. That's the symbol diagram that I would think of. We need to measure, of course, the relationship is to measure L and S. And of course, we have mass here. So these are my diagram. The next thing is how to define the problem. Defining the problem. Break down this into bits and pieces, and this will help you when you try to explain what you have in mind and how you're going to measure your data. So defining the problem. In defining the problem, you need to identify especially three things: the independent variable, the dependent variable, and the variables that you are going to be keeping constant, the ones that you're going to be controlling. So in our case here, L will determine how much the wooden strip bends. So L is the independent variable, while S is the dependent. S depends on L, right? Then of course mass is going to be the you'll keep mass constant, so that will be the controlled variable. So I'll go for L is the independent. L is the independent variable, and S is the dependent variable. Then the load of mass M is kept constant, or is the variable that you're going to control is kept constant. That's all for defining the problem. The next thing is to data collection, is to show us the method that you're going to be using to collect your data. Method of data collection. Break it into pieces, bits and pieces, and you'll have an easy time answering this question. Methods of data collection. How do we collect this data? Of course, you need to explain what the procedure that you're going to do to be able to collect this data. Of course, the first thing you have noticed that the wooden strip is held in place by the G clamp, is held in place on the bench by a G clamp. Is held in place on the bench by a G clamp. Of course, so that it does not topple, we hook a string with a hook where we are going to suspend the mass. A string with a hook is fixed to mass M and attached to the wooden strip at point P. point P. Very well. So we use a meter rule to measure both. A meter rule is used. A meter rule is used to measure both L and S. Of course, to measure S, capital S, lowercase s, to measure S, the meter rule should be held vertically. The meter rule is vertically clamped. Understand? And you should measure S when the meter rule has stopped oscillating, right? S is measured when the wooden strip is stationary, not oscillating up and down. Stationary. Very good. You need to take readings of S before and after the strip, and then find the difference, right? The reading of S is taken before and after loading. Don't forget you're using a vertically clamped meter rule. After loading the strip, and the difference found. Just the final reading minus the initial reading. Of course, you need to repeat the measurement of S in each time you come up with a new L. Repeat measurements of S for each L and get the average, and find the average. For S. Then of course you need to also measure B with a meter rule, and T with a vernier calipers. Vernier calipers. Very well. Don't forget, measurement of L should be taken on both sides. You should take the measurement of L on both sides of the wooden strip to make sure the strip is perpendicular to the bench. Those are some of the things you need to write. And when, of course, reading S, you should make sure the meter rule is not oscillating. Very well. I think that is sufficient. Next is method of analysis. How are you going now to analyze the results that you have gotten? Method of analysis. Okay. So you have your measurement of L, you have your measurement of S, you have measurement of B, you have measurement of T. So how do you now analyze your measurement? All right, so always go in the direction of plot your graph. So I'll say plot a graph, plot a graph of S in the y-axis against L cubed on the x-axis. How are you going to know whether S is on the y-axis or L is on the x-axis? You will know this by making S subject from the expression, this expression here. Remember this expression? You need to make S subject here. So to make S subject, you multiply S both sides. So it will be S is equals to 4mgl cubed upon BET cubed. Right? You have measured B, you have measured T, you have measured L. M is constant at G, and Young modulus. Young modulus, you're supposed to be able to determine it for you to use this expression. So you can now see you have gotten the relationship between S and L here. So that's what you're trying to test. Right. So here you are. So S is equals to 4m GL cubed upon BT cubed times Young modulus there. Of course, when you compare this to a straight line equation, m is equals to mx plus c, then of course x is s is y, x is L, and therefore the whole of this, that is the gradient, which is m, is equals to 4mg over bt squared Young modulus. So the whole of this is the gradient if you plotted S against L cubed. So you can say that comparing the two equations, that is this equation and the equation of straight line here, the relationship of S and L cubed will be valid if the graph is a straight line graph. If the graph is a straight line graph through the origin, So if you plot values of S and corresponding values of L and find that the graph is a straight line through the origin, then you have proved that the relationship of S and L cubed is odding. So you need to know how to determine the Young modulus. So to determine, you have to explain that. To determine a value for E, first you can see E is here. You have measured this, you have the value for this, you have the mass. and you plot the graph and you have calculated the gradient. Therefore, you can use this expression to get the value for E. So calculate for a value for E, calculate the gradient. Calculate the gradient. So the gradient is what you have written here, and therefore gradient is equals to 4mg bt cubed E. Therefore, make E subject. So E is going to be 4mg over bt cubed times gradient. Right there. So you have gotten your E right there. Next is safety precautions that you're going to undertake on this experiment. Safety precautions. Every experiment has got some precaution you need to undertake so that you minimize injuries. Safety precautions. You need to assess the risk of the experiment and describe precautions that should be taken to keep a risk minimum. I will go for, since we are having some masses and a string that is bending the wooden strip, then I will go for protective goggles. So I'm going to get protective goggles in case the wooden strip recoils and the string snaps. Recoils and the string snaps. I'm also using masses, so I need to put on protective shoes. Wear protective shoes in case the masses fall down. You could also use a mat so that when the masses fall down, they don't damage the floor. So those are some of the things that you need to use to write for you to earn the whole of these 15 marks. So bear in mind, this question is 15 marks. Question number 2. Before we get to question number 2, you can get solved paper 5 papers from this site, solvedpapers.co.uk. These papers are solved and you can access them from there. This is the site I have in mind, solve papers. You can of course come to A-level physics and go to 2019. You are solving a 2019 June paper. Come here and you will be brought to this page. Come to this page here. The paper we are solving right now is this paper here. You can download this paper, 5.1. You can also click here to get paper 5 solved in zip folder. When you click there, you come to this point here. Of course, these are papers 5. Paper 5 is the last one there. Of course, you can get paper 5 for physics and chemistry. 2019 November, 2019 June, 2018 November, 2018 June. 2017 is yet is still coming for physics, but chemistry is still in place. So we are dealing with June, so you need to come here and click this one, and you'll get this same paper that I'm solving in a soft form It's only 10 pounds. You can ask your parents to help you with acquiring these papers. Very good. Still, while at it, I also help students online. So I have an online tuition presence, tuition classes. So if you need my assistance, you can get me from at this site, spacademy.co.uk. The site that I'm referring to is right here. This is SP Academy, Soft Papers Academy. You can come explore the site and get to know more of our site. I need you to come here to the student guide. Click here to get a step-by-step student guide for how our site works. You can also watch this. You may also watch this video to get familiar with our online live classes. Of course, if you have made your mind and you need my assistance, I'll need you to log in here. I need you to log in. Need you to register if you have not yet registered. Of course, you select a group. You're a student. If you're a tutor, select tutor. Of course, and then of course you create your own account. Give us the correct email. You'll be send an email to activate your account. Once your account is active, you can sign in and come to your dashboard. From your dashboard, you can find a tutor. You can click here to find a tutor, and then we can help you get your A-star, the one you so much desire. So there you are. Get these papers from Soft Papers, and if you need my help, SP Academy it is. Let's go to question number 2. A student is investigating a rotary variable resistor, this one here. The variable resistor is connected to a battery of EMF E and negligible internal resistance. The battery does not have internal resistance. There's a ammeter there, there's a switch, and of course the variable resistor there. The student uses a protractor to measure the angle theta through which the spiral of the variable resistor is rotated and records the current. Of course, this varies the current. The experiment is repeated for different angles. It is suggested that I and theta are related by this equation, where k is a constant. There is a constant. A graph is plotted of the reciprocal of current on the y-axis and against theta on the x-axis. Determine an expression for the gradient. All right. So the graph that is plotted is 1 over I on the x-axis is equals to, of course, k over E theta. Of course, what you're going to do here is to make the I subject. Of course, you multiply or you divide both sides by current. You divide both sides by current. When you do that, you'll get E is equals to I is equals to k theta. Then you divide both sides by E. When you do that, you'll get 1 over I is equals to k times theta. So let me put this theta here, k over E times theta, right there. So I compare this with the straight line equation, y is equals to mx plus c, and therefore the gradient, which is this one here, because this is on the y-axis and theta is on the x-axis, then the gradient right there will be will be equal to, or my m will be equal to k over E is equals to k over E. So gradient is k upon E. That is what you are determining the expression for the gradient. The gradient is k over E. Part B, values of theta and I are given in Fig 2.3. We have theta in degrees and current in milliamperes. Then we have the reciprocal of the current here. So calculate the values of the reciprocal of current in Fig 2.3. Include the absolute uncertainties in I. So use your calculator and then find this. You just type 1 divided by 5.7 times 10 raised to power minus 3. This is milli. So when you do that, you use your calculator, you'll get a value of 175. 175. So you write your 175 there. You need to find the absolute uncertainty. To find the absolute uncertainty, you need to find the reciprocal of the current on the higher value of the current. So you will get 5.7. The uncertainty of the current is this. We want to find the absolute uncertainty of the reciprocal of the current. So we add 1, we find the greater value. You can also find the slower value, it doesn't matter. There you get 5.8 milliamperes. So then now, of course, you come here, you find 1 divided by 5.8 times 10 raised to power minus 3. When you do that, then you're going to get a value. Let me see what I get with my calculator here. This is 5.8 exponential minus 3. I've gotten 172. And therefore, uncertainty is equals to the difference between this value and this value. So 175 minus 172, this gives me 3. So my uncertainty is plus or minus 3. Go to the second one. You find the reciprocal of the current, which is 4.7 times 10 raised to power 3 minus 3. What you get is 213. So you get 213 there. Let's get the uncertainty. So you get this 123 minus you add this to here, you get 4.8. So minus 4.8 times 10 raised to power minus 3. Of course, when you calculate this nicely, you're going to be getting 4. So your uncertainty here is 4. So that's how you do the rest. So let me give you the values that I've already calculated for the rest. Plus or minus 6. This is 286 plus or minus 8. This is going to be 323 plus or minus 11. And then this one is 370. The smaller the bigger the reciprocal. I hope you know that. Plus or minus 13. So you have all values there, of course. So you're told to, part C, you're told plot a graph of the reciprocal of current against theta, against the angle right there. So you're supposed to include the error bars for the reciprocal of current right there. So the error bars are the absolute uncertainties of the reciprocal of the current. These are what is going to help you plot the error bars. Okay, so let's plot the graph. You're so taught, once you plot the graph, draw the line of best fit. And what's the exact straight line of your graph? Both lines should be clearly labeled. Determine the gradient of line of best fit. include absolute uncertainty. You come into that. Let's first plot the graph. Let's first plot the graph right there. The graph is here. This is the y-axis is current, reciprocal of current right here, and the x-axis it is angles theta. You may notice the graph is not starting at origin, so this is 80, this is 100, and in between here I can slot in 90 here. 100, this is 110, this is 130, this is 150, 170, 190, this is 70, this is 90, then there is 180 here, this is 200 right there, this one is 220. This is for my purpose when I'm plotting the graph. This is 260, 280, this is 200, and this is 300, this is 320, 340, 360, and so on and so forth. You got the idea. So let's do the plotting. The first value is 95, and the first value is 95 on the x-axis, and 175. So 95. So 95 is here. That is 95. Then 175. This is 70. This is 180. So 175 is there. So right there. Use crosses to do your plotting. The next one is 115. This is 110. So 120, 115 is there. And 213. That is 20. So this is 213 is there. Then we come here. So right here. Right there. Next one is 135. 135 is there. And then 250. 235 and 250. Right there. Next value is 155. 155 is there. And 286. 286. So 286. Each one of these is 2. So 286 is here. That is correct. That is 280. This is 282, 284, 286. It's there. It's right there. The next one is 175. 175 is there. That is 175, 175, and 322, 323 actually, 320, so 323, let me see, it's there. Okay, next one is 195, the last one, 195. 195 is there, so you go up 195. 195, you get 370. 370 is there. Very good. So we have our graph plotted there. So So now I'm going to draw my graph. I've just minimized it so that it looks visible. So I'll draw the line of best fit. Hope I'll get it right. I hope that is the line of best fit. I've done my best. Right there. It's line up by best fit. Right there. Does not pass through every point. That line. So the next thing we are told is to include the error bars. So the error bars are this, plus or minus. So you'll draw 3 on one side, upper side of this point, and 3 down on the downside of this point. Let me change color. This is we use green. So for the first one, the error is plus or minus 3. So this one is so each here is from here is 2. So from this is 1, 2, 3. So from here to there. That is my first error bar. The next error bar is plus 4. Plus 4 from here. 1, 2, 3, 4. So from 4 is from there to 1, 2, 3, 4 to here. There. I think this is not correct. It's in the middle. That is 4. The next error bar is 6. So 2, 3, 4. 6 is there. The next one is 8. From here, 4 steps. 1, 2, 3, 4. 1, 2, 3, 4. And they're so in the middle. Right there. The next error bar is 11. So this is 1, 2, 3, 4, 5. There. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. One, 2, 3, 4, 5. 5 is up here. Draw this line. There. Then the other one is 13. From here, 13. So 10, 13 is there. 10, 13 is there. So I draw this. That's my error bar. Then I draw now. I'm supposed to draw worst acceptable line. I've drawn the best line of it, so I need to draw worst acceptable line right here. So the acceptable line, the worst acceptable line should pass through all the error bars, right? So let me zoom out. All right there. So let me now draw my worst line, worst acceptable line. Just start from here, go through all the error bars. Can either be on top or bottom. This one is not going nicely. Hopefully, still not good. Should go through all the error bars. Guys, be patient with me. I'll get it right. Hope that's good. It is touching all the error bars, I suppose. Something like that. So that is our worst acceptable line. Right there, you can see it. Then the next point is you're supposed to determine the gradient of the line best of fit and include the uncertainty in your answer. So the uncertainty will be the difference between the line of best fit and the gradient of the worst acceptable line. So pick 2 points of your choice and work out the gradients. I'll just show you how I worked out my gradients here. So I'll start with the line of best fit. Line of best fit. I've picked 2 points, 92 on the line, not the lines from the coordinates. The lines, these points are picked from the line of best fit, 370. Then of course I'll get the gradient. Gradient is equals to 370 minus 170 upon 200 minus 92, and what I get is 185 as the gradient. So gradient of the worst line, sorry, let me call it worst acceptable line, worst acceptable line. Okay, I'll pick this point, 98 and 180, and the other is 194. These are the coordinates that I'm going to use, 370. So gradient is 370 minus 180, 194 minus 98, and I got 1.98. Therefore, absolute uncertainty is the difference, 1.98 between this, doesn't matter which one is greater, minus 1.85, and what I got is 0.13. Therefore my gradient with uncertainty is this 185 plus or minus 0.13. There you are. That's how you get the gradient. So you get the gradient and the absolute uncertainty. Okay, part D. And before I forget, you're supposed to label. You're told to draw the, so both lines should be clearly labeled. So this is the green one. The green one is the worst acceptable line, and the red one is the best or line of best fit, line of best fit. You need to label that. That is required. Part D, you're told as the student measured the EMF of the battery twice. The student's values are 9.6 volts and 9.2 volts. Determine the average EMF of the battery, include an absolute uncertainty. So average, you just add the two and divide by 2. 9.6 plus 9.2 divided by 2. This will give us 9.4 volts. The uncertainty, delta E, is the difference between the two. 9.6 minus 9.2. This gives us 0.2. And therefore, the EMF is 9.4 plus or minus 0.2 volts. Part E, use your answers to A, C. Part 3, D and D, determine the value of K, include appropriate unit, right? We find that gradient in A is equals to K upon E. If you've forgotten, I'll take you back there. Gradient is K upon E. So we use for A and C part 3. C part 3 is the gradient that we have gotten here. And D, okay, what we have gotten here. So we had found that gradient is equals to K upon E, and therefore we want K. So K is equals to gradient times E. Therefore the gradient we had gotten is 1.85 times E, which I've gotten here to be 94. 9.4. And therefore K is can include the units. Let's include the units here. This is per ampere, degrees, per ampere degrees, times 9.4 volts. So that we are good to go. So this is going to, when you multiply this times this, you get 1. This is not 1 point, this is 17.39. And of course, this is going to be volts over amperes per degree. But we know that volts, we know that voltage is equals to current times resistance, and therefore resistance is equals to volts over current. And this is going to be, unit is going to be volts over amperes, and volts over amperes is equals to ohm. So then this you can write it as 17.39 ohm per degree. So that you write here 17.39. We need an appropriate unit. Ohm per degree. So this is basically ohm per degree in words. So there we have our K. We are taught to determine the percentage uncertainty in K. Of course, we have gotten K from calculating the gradient. So percentage uncertainty of K is delta K over K percentage. Of course, this is going to be equal to the percentage of the gradient. Let me call it this over gradient plus the uncertainty of the EMF over the EMF, and of course times 100. Times 100. So the uncertainty of the gradient is here. The uncertainty of the gradient is 0.13, the uncertainty, and of course the gradient is 1.85. The uncertainty of the EMF is 0.2. Don't forget that we have gotten K from the gradient, multiply the gradient and the EMF. So that is what you're going to be using here. So 0.13 over 1.85 plus 0.2 upon 9.4 times 100. This gives us 9.23%. So the percentage uncertainty is 9.23% for K. Lastly, F, determine the angle through which the spiral of the variable resistor is rotated so that the current is 10 milliamperes. Include an absolute uncertainty in your answer. Of course, the equation, we know the equation is I K theta. We want theta, so theta is equals to EMF divided by current and K. And of course, you've gotten the EMF here is 9.4 over, we're looking for the current of 10 milliamperes, 10 times 10 raised to power minus 3, times the value of K, which is a constant, which I've gotten. Value of K is here, 17.39. 17.39. When you work out this nicely, you're going to get 54 degrees right there. So let's find the absolute uncertainty of the angle theta. So delta theta divided by theta is equals to uncertainty of EMF divided by EMF plus the uncertainty of current divided by current plus the uncertainty of K divided by K. Of course, we found this one to be 0.2 divided by 0.4 plus the uncertainty of current is 0.1, so 0.1. Where do we get the 0.1? 0.1 is right here. The uncertainty of the currents are 0.1. So 0.1 over now 10 milliamperes plus the uncertainty of K, which is 9.23, and the value of K, which is what is the value of K? The value of K, we have gotten the, of course, can do this in this way. We know that K is, we have gotten the percentage uncertainty, so we don't use this one here. We need the absolute uncertainty. So let's find out the absolute uncertainty of K. The percentage uncertainty of K is 9.23. And therefore, the absolute uncertainty of K, we divide both sides by 100, because this is basically delta K over K times 100 to convert it to percentage. So we divide both sides by 100, divide by 100, divide by 100. So we'll get this 9.23 over 100. So that is the absolute uncertainty of K, which is 9.23. 9.23 divided by 100. Of course, when you work it out, you find that delta theta over theta, the absolute uncertainty is 0.124, right? And therefore, we want absolute uncertainty. Therefore, delta theta is equals to 0.124 times theta, and theta here is 54. We have found theta to be 54, so we just multiplied by 54. So the absolute uncertainty is 6.7. Therefore, our value for theta is, when the current is 10 milliamperes, is 54 plus minus 6.7. And of course, this is going to be degrees, as you can see right there. So that is it, how you solve this paper 5. I hope this has been of help to you guys. I encourage you to consider subscribing to my channel. When I do more paper 5s, you will be notified. Please get more solved paper 5 from this site, Solved Papers, solvedpapers.co.uk. Of course, if you need my help, you can get me in spacademy.co.uk. Share this video with your friends if you find it usewful, and I'll see you in my next video, guys. Cheers.